All right. So, lecture 2, postulates of quantum mechanics. There's 4 postulates that we're gonna go through. I think in the first lecture, I'm going to focus on the first 2, describing the state space and configurations and the evolution of a system. In the next lecture, I'm gonna focus more on the third and fourth postulates, measurements, and compositions of a system. And in particular, part of my focus for this lecture is the second postulate, the evolution of the system. I want to figure out how things evolve. And what I want to get to, is the evolution of the simplest non-trivial system that I can think of. And once I have the evolution of that system, I want to extend it to a larger system by using compositions of systems. And this is going to be what I introduce it in this lecture as a quantum coin, which is just going to have 2 states, heads or tails. I'm going to then extend it to what I call as spin systems. And it's going to be a composition of many heads, tails. So you can think of like a collection of coins, and it's either going to be heads or tails, and you're going to see how it evolves. And but for the introduction, I think it's instructive to just look at the simplest case and see how it evolves. We're going to almost get to the evolution, but at the end it's going to be an optional exercise, and then I'll cover the solution when we meet next time. And in introducing the postulates of quantum mechanics, I really want to make sure they're well motivated and they're not just abstract statements. I want to draw comparisons with classical cases. And throughout the lecture, this is what I want to do. I want to look at the classical case and then compare it to a quantum case. So in the first postulate, we want to look at what is our state space and what are our configurations. And in mathematical terms, something that people are most familiar with from classical mechanics in state space and configuration is just like projectile motion. And that's just throwing a ball, and then Newton tells you how it's gonna evolve. And in that case, you have, you can do it in 2 dimensions, or more generally in 3 dimensions. That's the most typical, or that's the dimensions that we live in, 3 dimensions, and you throw the ball. And to figure out the evolution of the system, you need the evolution or the configuration of the system, you need 2 pieces of information, the position and the velocity. So this is denoted here by P is the position and Q is the velocity. So it's a point in space and an initial velocity. And then with F, d squared x dt squared equals ma, or F. Then given this information, you can track the evolution of your particle. And typically mathematically, or more rigorously mathematically, this space, the state space, is typically given as a tangent space of some manifold, which encodes both the position, P, and the velocity, Q. So 2 pieces of information for, if the manifold is just the real space, then the tangent space is, it's equivalent to R6, where the information, it's 3 dimensions here for the position and 3 dimensions here for the velocity. And this is in classical mechanics, this can be abstracted more, and then you can talk about symplectic manifolds and symplectomorphisms for the evolution of your state space and stuff like this. But I mean, here this is already getting too complicated. So when I think in the classical case, I actually think more in terms of probability. It's possible to take the picture that we had before and convert it into the quantum mechanics, but in that case you're moving from something infinite dimensional to something much more infinite dimensional. So in that case things get a little bit hairy. So I actually, when I'm drawing analogies between classical and quantum, I actually like to go to something that's way lower dimensional, way lower degrees of freedom. So I actually try to draw most of my analogies and inspirations from probability. And this is something that I mentioned briefly in the previous lecture, where I talked about the countable additivity property of probability spaces. And moreover, this analogy to probability, I think, is useful because in quantum mechanics, what you'll have is that the system is determined up to a probability. So it's also a good way to compare the classical probability and the probability you get from quantum mechanics. So in the setup for the classical probability space, you're given 3 pieces of information. One, the set of all outcomes, which is S. B, or this calligraphic B, is the set of all events, which are subsets of S. And the probability function, which is a function from the set of events to the interval 0, 1. And then you have some axioms to actually make this a probability space. And one of them was the countable additivity that I described earlier in the previous lecture. But in terms of state space and configuration, you should think of the state space as S, the set of all outcomes, and a configuration is just a specific outcome in your state space. So this is the analogy that I want to think about. And there's a small caveat about the set of all events. If S is countably infinite, then you need some care to define this set of all events. It's non-trivial to do it, but in this case, I will just deal with discrete and finite systems. And in that case, the set of all events, so here the outcome space, in this whole lecture, I'm just gonna focus in the case of a coin flip where you have 2 possible outcomes, heads and tails. And in here, the set of all events is gonna be just all subsets of the set S. So you have nothing happens, everything happens, heads happens, tails happens. And the probability function here, you can just, for a fair coin, it's just gonna be the number of elements in E, the event, which is a subset, which is an element in here, divided by 2. So for instance, the probability of heads, which is really just the probability of this event, just the subset H is gonna be 1/2. And here, S is gonna be my state space, and the configurations are gonna be heads or tails. So this is, I'm bringing it back down to the smallest non-trivial thing that I can think about. So this is the way that I'd like to actually concretely think about quantum mechanics. So, and now that we get into the state space and configurations for the quantum case. So here, we're moving into linear algebra. And actually, So the state space here is going to be given by a Hilbert space. And this is going to be a complex vector space with an inner product. So it's just going to be in here, it's just going to be a vector space. And depending on your system, on the degrees of freedoms that you have, then and the number of configurations, it's going to give you the dimension of the Hilbert space. If we went originally with the just R3 and just like regular space, the Hilbert space in that case is going to be infinite, the dimension of that Hilbert space. And even trying to describe configurations gets a little bit tricky. So but it's possible to actually work with finite dimensional Hilbert spaces where the linear algebra is just the basic linear algebra. For infinite dimensional Hilbert spaces, everything gets a little bit more subtle, and the theory of quantum mechanics gets, in my opinion, it gets muddled with the technicalities from the mathematical theory of Hilbert spaces. So here, we just want to focus more on the interpretation of quantum mechanics. So this is a choice that I'm making, and here we have this inner product that comes with the Hilbert space. Bless you. Where in here I denote the dot product of two vectors by this notation, and then if I flip the entries of the inner product, then I get the complex conjugate of that dot product. And this is part of the complex structure. And moreover, we have, using the dot product, actually this should be like this. Using the dot product, we can also define the length of a vector. And this is just going to be the dot product of the element with itself. And so our state space is going to be this Hilbert space with this inner product, and the configurations are going to be vectors in the Hilbert space, so that the length of the vector is the length square, or the dot product with itself is equal to 1. So this is going to be our configuration space. And the interpretation, so this is going to have a probabilistic interpretation. That's why it's equal to 1. And it says that the total probability is equal to 1. So what you want to think about is that a vector, you can always, if you have a specific basis, you can write it as a linear combination. Actually, I'm going to do C1 times E1 plus dot 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 C2 Cn E n. So you can write as a linear combination of some basis vectors E1 through En. And these basis vectors really are going to represent certain configurations. And the fact that the norm square is equal to 1 means that the probability that you're in one of these specific configurations is going to be equal to 1. So you have to be somewhere. And this is similar to the case in probability, that the probability, if we go back, and here, one of the axioms of probability is that the probability of the whole space is equal to 1. So this is a similar condition, that the total probability adds up to 1. So we impose this condition that the norm squared of a vector of a configuration is equal to 1. So now let me take a moment to introduce bracket notation. So this is notation that is most popular in the physics community. And really what it is that instead of writing in math, typically you denote a vector by this arrow on top, and instead of writing the arrow on top, you actually kind of just do this. Like, this is a cat, right? The ones on the right are cats. So the way that I think about it, I have this arrow here, and then I just move it here. So it's just the same notation, and that's the notation I'll often use. It's either going to be this, or it's going to be coordinate notation where I express this. This is also, I can also express this in coordinates, kind of like v1 and v2, if it's a two-dimensional vector. So these are three equivalent notations. In here, you do have to choose a basis to go this way. And this notation here is basis independent. And then if we have the arrow going the other way, this denotes a bra, which is a dual element of the ket vector. And really, the way to think about this, the kets are going to be column vectors, and the bras are going to be row vectors. And again, this is if you choose the same basis. So this is just going to be notation. Kets are row vectors, and bras are, no, column vectors are kets, and bras are row vectors. And the advantage of this notation is that you can succinctly denote row versus column vectors, and it's a notation that is independent of the basis. Whereas if we wanted to do the rows and column vectors in here, then this really depends on some basis. In here, actually, I don't know what I have this is going to be norm squared. And 1 if it's a configuration. And here additionally we have a geometrical interpretation that this is going to be the dot product. If you apply the bra to the ket, then you have that this v, using the row and column notation, then it's just going to be v1 v2 times v1 v2, and this is going to be v1 squared plus v2 squared, which this is v squared. And if it's a configuration, it's 1. So here we have that bras actually act on kets. So you can compose a bra and a ket, and it's going to be an inner product. And this is just a row vector times a column vector, and it's what we are familiar with from linear algebra. And then there's this geometrical interpretation that similarly, if you act this bra with this ket, then this corresponds to the projection of W onto V. And this is, again, the typical interpretation of dot product. So these are going to be projection operators. Yeah.
Just curious, so the second bullet point, H star equals, is that HAM?
Hom.
What?
Hom. H-O-M.
Oh, HOM. What
Uh,
does that stand for?
it's the, what does, 1 second. I want to say, home dual space. It's the, let me just do a notation. This is the set of linear functionals from H to C such that F is linear. And I just call it hom, but it's not homological, it's not homomorphism, it's and it's
Homotopic? I know that's another home word.
homotopic, yeah, dual space, home, dual space. So this is, yeah, it's home. But what does home stand for? But it's the dual space, and the technical definition is that it's the set of linear functionals, or the set of functions from H to C, such that F are linear. At this point, one can't help but to quote Shakespeare, right? A rose by any other name smells just as sweet. So that's the sweetness, the definition. So, but it's a dual space. Sorry, I forgot. It's escaping my mind. But good question.
Yeah, I've never actually seen that before.
Yeah, it's I think it's more math notation, and it's typically used for, I think, yeah, maybe you're more familiar with this notation for dual spaces. Yeah, so, because the thing about this notation here stands for like this linear maps from H to C, but this notation actually generalizes a little bit more, where you can have another vector space here. So this could be some other vector space, and then this would be the linear maps from H to V. So, and then this, you can then show that this is a homeomorphic to H star tensor V. But
it might be a home functor.
Hum functor, but what does hum stand for?
It becomes category theory.
Yeah, so it's homomorphisms, that's it. Homomorphisms from H to V, thanks. That's the home that we were looking for.
Yeah, it's a set of linear maps.
Yeah, homomorphisms. Yeah, homomorphisms. All right. We cleared that out. But yeah, that notation from home is just so that you can add something else as the target space. But we're just interested in the target space being the complex space, a one-dimensional vector. So anyway, so far so good?
I just want to say, the components of your products should be conjugated.
Yeah.
Just to be clear.
Yeah. These are going to be the complex conjugates. Yeah. And then this would be this, and then it is PI V2. Yeah. All right. So here is the idea that if to go from roughly, which this is not always the case, it's not an exact recipe, but the way to think about it is that you can take a classical configurations are going to become an orthonormal basis in the quantum case. So for the quantum coin, I can take my Hilbert space where that has a basis given by the heads and tails, by heads and tails. So these are going to be H and T are going to be orthonormal vectors, and meaning that their dot product is 0. The dot product of H and T is going to be 0, and my Hilbert space is just going to be a linear combination of these two configurations, H and T, where these are just going to be complex coefficients, so we're in a two-dimensional vector space. And again, this is the smallest dimension we can get where things are non-trivial. And for instance, in here, one particular example of a configuration is this V, where it's just a linear combination of this. You can actually check that if you take the dot product, that the dot product with itself is equal to 1, meaning that it lies in this unit circle. And it's given here. And if you do the dot product of V with H, you get this 3/2. And if you do the dot product of H with T, you get this 1/2. So this is the picture of that dot products are going to be projections. And then also we have that the interpretation that for this V vector, the interpretation is that it's in a superposition of two states, H and T. And that means that the probability of finding the vector V in H is actually going to be given by this quantity, and the probability of finding V in this state is going to be given by this quantity. So as a quick in-class exercise, I'm going to ask you to compute these probabilities, H and T, just to check that you're following the notation. And we should have that the probability adds up to 1. Joseph, do you have the probability for H?
I think so.
What is it?
I think it's 3/4 for heads and 1/4 for tails.
Yep. Let's see. 3/4 and 1/4. Does everyone agree? All right. So yeah, it's just dot products. And then another quick question for the class. In this picture here, where do you see the orthonormal condition? Anyone?
Orthonormality of basis T and T.
Which graphically is, yeah, that this is a right angle. So in this diagram, there's this unit circle, meaning that if a configuration lies in here, that's a configuration, and that that these classical configurations are orthonormal is that this is perpendicular. Yeah.
So you have written that the configurations become an orthonormal basis.
Yeah, the classical configurations.
Is that like, so the configurations that you had before, they were like, you have both P and Q.
Yeah,
that's
in
like-
in T3.
Right, so that's like two things that are each part of their, like they each make up a thing in the state space.
Yeah.
So is it that each, like a whole configuration has an orthonormal basis, or like the elements in the configuration?
The element each. So in that case, it's actually you actually just take the p coordinates, and each of one of those coordinates is going to be a basis vector. So you're going to take R3, and each element in R3 is going to be a basis vector. So you're going to have a Hilbert space that has a basis, an orthonormal basis, labeled by points in R3. So that's a really big Hilbert space. And that's when it gets messy to work with it. And then you actually have to work to find the appropriate Hilbert space. This recipe of just taking the configurations, the classical configurations, and then turning it into a Hilbert space breaks down in that case, in the infinite case. And so in that case, you actually look at L2 of R3, which is the square interval functions on R3. And then that's still an infinite dimensional space. And then the linear operators there are differential equations. And then you just move on to PDEs instead of linear algebra. And so it gets a lot more messy. Does that make sense? So again, I just want to do the simplest thing. So that's the state space for the quantum system, the way to think about it. Now we are looking at the evolution of the system of the quantum case, and again, I want to start with the classical case, and sticking with so in here, I'm going to denote my configuration at time t by x of t, and in the probabilistic case, it's going to be a probability vector, where each entry is the probability of being in each of the states, in each of the configurations, especially in the finite case. So for the coin flip, you have that this configuration at time t, it's going to be the probability. We're going to see how the probability evolves for each of the configurations, h and t. And the evolution is given by a differential equation or a difference, depending on discrete, whether you're in continuous time or discrete. If you're in continuous time, the evolution of the probability is going to be given by this differential equation, where you take the derivative of the entries and you take this vector and multiply it times a matrix A. In the discrete case, it's similar. The evolution of one step is given by the probability at the previous step times the transition matrix P. And this is the theory of Markov matrices. And this is what I like to draw an analogy to. And in particular, one specific example is this coin flip. This you can start in a configuration pi 0, where the probability of being heads and tails is equal, 1/2 and 1/2. And then the process of just flipping a coin is just going to be given by this transition matrix. And it really tells you, so for instance, in here, this element, this is really equal to the probability that you go from heads to tails. And it's going to be 1/2. And so I label this by heads, tails, heads, tails, heads, tails. And this is going to be my transition probability. And I can also write this as a diagram where the probability of going from heads to tails is 1/2, tails to heads is 1/2, heads to heads is 1/2, and heads to heads is 1/2. And then if you start from equal probability of heads and tails, then the probability at the next step, if you multiply everything out, you'll actually see that it stays 1/2, 1/2. But this is how the probability is going to be evolving classically. And one thing to consider in this evolution is that the matrices that give you this evolution of the probability vector actually have to satisfy this Markov condition. And this Markov condition is a conservation of probability. And in the discrete case that we just saw, this condition means that the rows, first of all, that the rows add up to 1, and that the probabilities, the transition probabilities, are greater than or equal to 0. So in particular, the fact that the probabilities are greater than or equal to 0 is because the interpretation of the entries is that they're transition probabilities, the probability to go from one state to another, so it has to be a positive number. And then the Markov condition is that the rows have to add up to 1. So this adds up to 1, and this adds up to 1. And this condition is going to preserve your probability, so you're not going to lose any probability. If it doesn't add up to 1, then the sum of the elements of pi 1 may not add up to 1. Yeah.
Is pi 1 still a row vector at the end?
Yeah. Thanks. One half. Yeah. So if we don't satisfy the Markov property, then we might be losing some probability, and the elements of pi may not add up to 1. And in the continuous case, you have a similar condition. Your entries are going to be aij. And in this case, the non-diagonal entries are going to be positive, and the diagonal entries are going to be negative, and the sum of the rows have to add up to 0. And you can actually check that that condition will preserve your probability. So going into the quantum case, we want to do something similar. And I want to look at the discrete evolution. And again, this is going to be, the evolution is going to be given by linear transformation by a matrix U. And in here, I denote psi of t to be a configuration at some time t. And I consider the discrete evolution where the evolution at time t plus 1, the configuration at time t plus 1 is given by u times psi of t. And in here, the question that should jump out to you is what's the equivalent of the Markov condition. And again, the Markov condition is a condition so that probability is conserved. We don't lose any probability. And in this case, that's what we want to determine. What's going to be the condition on U so that probability is conserved. And I'm going to look specifically at this quantum coin and started from this configuration that we saw. And in here, if I take the dual vector of psi of t, I get this row vector. So here I'm writing it in coordinate notation, where I choose a basis that h is equal to 1, 0, and t is equal to 0, 1. So I have to make this choice, and then I can write this equality. And then the dual vector is going to be this. The complex conjugate of real things are real. And then you can actually check that the total probability is equal to 1. And now let's assume that our transformation, our linear transformation, is in this basis is denoted by A, B, C, D. Then my evolution of at time t plus 1, my configuration is given by this product, by this transformation. And we want to figure out what this dual vector is in terms of u, and psi of t, the dual one, so that we can compute that the total probability remains equal to 1. So this is the goal. We're trying to figure out what conditions we need on U so that at time t plus 1, this condition is still true, that we have total probability equal to 1. So let's actually work it out explicitly. So we have in coordinate form, we multiply things out. We have this. If we write it in this basis, h and t, we have this. And this is going to be psi of t plus 1. And we know how to take the dual of this. Just flip it and take the complex conjugate. And here we have this. And then you can actually check that this row vector is equal to the product of this row vector times this matrix, which is related to our original U matrix. And it's just a conjugate transpose. So you flip it on its diagonal and take the complex conjugate of the elements in the matrix. And this is noted by this. So you have that this complex conjugate of this matrix is acting on this vector. So now we have this action to evolve the vector, this action to evolve the dual vector, and we must have that this condition, the total probability, is equal to 1. And now I'll leave it up to you to figure out what that condition is. And I can rewind if you guys need me to, or if you have any questions, I can clarify.
In your second line, should the second bra be side of T?
Yep.
Yeah, okay.
Thanks. Any shots?
Is it that U must be unitary?
What does that mean? Fancy words. So U must be unitary or Unitarian. So what does that mean?
It is the conjugate transpose of U with itself equals 1. I mean, or I guess I could say the set of columns. The different columns, I guess. That's how I kind of see it.
Yeah, you have it right there. Here's the hint. This times this is equal to identity. Yeah.
Yeah.
The identity matrix. Yeah. So then we have that this is equal to and then since we already had that the total probability of that is equal to 1, we're going to have 1. So here, I really just wanted to motivate this unitary condition. So the evolution of a quantum system, you're going to have a unitary matrix. And in the continuous case, you also have the evolution is given by a linear operator. We have this Schrodinger equation. You throw in this I h bar. This is for historical reasons, although there might be more to it, but for now we'll just say it's historical reasons. Mathematically, most of the times I just set h bar equal to 1, but this I actually matters. And you can actually just separate variables here and solve this differential equation, and it's equal to this. And this is just going to be the exponential of this matrix. And then by the same idea of conservation of probability, this must be a unitary operator, a unitary matrix, this exponential. So this must be unitary. And this really implies that this has to be equal to 0, this property. And then it means that the conjugate transpose of H has to be equal to H. And that means that H must be Hermitian. And this is then a condition for the evolution of a quantum system. H must be Hermitian. So this is what we'll start with next class. We're gonna consider the dynamics of this quantum coin, and here I'm choosing a particular Hermitian operator with a parameter delta, and here, due to the Hermitian condition, this delta must be real. And the question is, what's going to be the evolution of this quantum system? And really, it becomes into a question of how do you actually even take the exponential of a matrix. So we'll discuss that, and we'll get into some of the properties of Hermitian matrices to do this. For this is going to be an optional problem. Just compute this. And really, the real question that we want to answer is, what's the probability that the configuration at time t is equal to tails at time t? So this is what we're trying to compute. So these are optional problems for you to work on, but I'll do this computation on Monday. That's class.